device is working now. So anyway, the magnitude is the length, okay? And the magnitude can be represented like this. PQ with a little arrow thingy on top, and 2 bars like that, okay? And the magnitude is equal to, it's just like the Pythagorean distance formula. You just take the x coordinates, x1 minus x2, and square them, right? The difference between the x1 and x2. And it doesn't matter, like in this case, whether you subtract x2 minus x1 or x1. Whoa. That's my Jason Maris son, okay? Okay, I can't talk right now. And then y1 minus y2 squared. Okay, yes? No, maybe? So we'll do some examples in a minute. Right? So that's just the distance formula. And that's the magnitude of a vector. That's how you find it. Okay? Usually you represent vectors with bold letters. Okay? So if I want to represent, so sometimes instead of calling this PQ, they'll call it vector V. And they'll have like bold, small case letters, kind of like that. Okay? So here's vector V. Sometimes they'll say vector U, and it'll be like a bold lowercase. They'll have vector W with a little w. Don't ask me why. So vector, it'll look something like that. So if you see a bold-faced lowercase letter, that'll be a vector. Okay, so it's like vector V, vector U, vector W. Okay, and so on. What else? So, congruent vectors are, you don't really have, yes, ma'am?
Are the things above, like the PQ, when you write the vectors, are those just normal arrows?
Yeah, they only have like a one, not like both.
Yeah.
Yeah, there's only like a top.
So that's how, like, when you write vectors, you just do
Yeah, with a little,
okay.
yeah. Okay, but meaning it goes from P to Q.
Yeah, okay.
And then vectors are equal, okay? Vectors are equal. Vectors are equal if they have the same magnitude and direction. If they have the same magnitude and direction. Good? So, like if you think about, anyone ever see like the Blue Angels or anything like that? Anyone? Those guys that fly air jets, you know, and they're flying in formation, okay? Those guys are flying with equal vectors, right? Otherwise they crash into each other, you know, and it's like amazing how close they could stay to each other and fly really fast like that, because they're going the same speed usually, you know, and in the same direction. And it's pretty cool to see. Okay, so show that UV. So show that U. I'll make that U equals V. If U goes from initial point P, so U goes from P, which is at 0, it goes from 0, 0 to Q, which is 3, 2, and 3, 2. And V goes from R, which is at 1, 2, to S, which is at 4, 4. Okay? So the first thing you have to do is find the slope. Okay? So the slope of u, because by finding the slope, you could show that they're going the same direction, right? Okay? So that would just be y2, right? You find the slope just like you're finding normal slope. So y2 minus y1 over x2 minus x1, so that's 2/3. You understand what I just did? Okay? I just kind of did that in my head. And the slope of v, right? Slope of v is equal to 4 minus 2, right? 4 minus 2 over 4 minus 1, right? Which is also equal to 2/3. So they're going in the same direction, right? They have the same slope, but I also have to find so that they have the same magnitude. So the magnitude of u, which you could write like this, okay, is equal to x1 minus x, the square root of x1 minus x2 squared, which is 0 minus 3 squared plus 0 minus 2 squared, and that comes out to be the square root of 9 plus 4, is that correct? Which is equal to the square root of 13. And v has a magnitude of square root of 1 minus 4, and again it doesn't matter which way you subtract since you're squaring, plus 2 minus 4, which also I think comes out to be the square root of 13, doesn't it? Negative 3 squared is 9, and negative 2 squared is 4. So that's equal to the square root of 13. So the slopes are equal, and the magnitudes are equal, so those vectors are equal. Right? And if I were to graph them, which you can do, okay? So if I were, let me just show you on a graph. Two-headed arrow, different color. No, we'll keep it green. So if I were to graph those two vectors, okay, we'll make them red. Get rid of that arrow. So from P to Q, the way you graph vectors, I'm kind of getting ahead of myself here, but I'd go from 0, 0 to 3, 2. So if I were this for my graph, 3, 2, so that vector would look something like this, right? So there's vector u, and vector v goes from 1, 2, let's see if I could, 1, 2, to 4, 4. 1, 2, 3, 4. 1, 2, 3, 4. My scale's kind of, not great. But if I graph those two, it should show that they're about the same length there. I faked it, okay? Same length and same direction, right? Those are the blue angels. Right? Okay, there they go. All right, so that's that. Component form of a vector. Component form of a vector. I know it's a lot of it's just kind of a lot of notes here. Okay, so component form is looks like PQ. This is vector PQ. The way you find component form is you go little q1 minus p1. I'll show you what this means in a minute. Okay, p1, comma, q2 minus, that's a q. q2 minus p2, which is equal to b1, comma, b2. And this is called the horizontal component. called the, guess what? The vertical component. And so what this means is you take the endpoint of the first vector and the endpoint, excuse me, the x-coordinate of the endpoint and the x-coordinate of the start point, and you subtract them. And this is the y-coordinate of the endpoint, and this is the y-coordinate of the start point. Okay? So I'll show you in a minute. So find the component form. We already did it in component form of the vector PQ if P, I'm just going to make something up, negative 3, 1, and Q is, if P is negative 3, 1, and Q is 5, negative 4, or something like that, okay? So all you do is you put little arrowy brackets around that, and Q1 is 5, right? So here's Q1, it's just like X1, X2, Y1, Y2. So here's Q1, here's Q2, here's P1, and here's P2, right? So I just subtract. So Q1 is 5, right? And P1 is negative 3, so I'm going to go 5 minus negative 3, comma, negative 4 minus 1, right? And I simplify that, and I get that that is 8, comma, negative 5. Yes? You understand that? Okay? And then if I wanted to graph that vector, I could graph the vector from negative 3, 1 to 5, negative 4, or I could put it in standard, what is called standard position, okay? And the way I graph something is in standard position is starting at the origin, okay? So if I were going to graph this vector in standard position, I would go over 8, 1, 2, 3, 4, 5, 6, 7, 7, 8, and I'd go down 5. 1, 2, 3, 4, 5, and I put a point there, okay? And then I would put in my vector, okay, from the origin to that point. So there's vector PQ in standard position. So standard position, standard position just means it starts at the origin. Starts at origin at 0, 0. Okay? I could also graph this vector going from the point negative 3, 1 to the point 5, negative 4, right? And it would be, it should be parallel to that vector, right? So I could go like that. Okay? What else do I have to talk about? Magnitude. Another way you could write the magnitude. The other way you could write the magnitude is by taking two other ways you could write the magnitude of V. Okay? Magnitude of V is equal to, it's really the same thing, x1 minus x2. But you could also take the square root of V1 squared plus V2 squared. So if I wanted to find the magnitude of this vector right here, so say this is, we'll call PQ vector V. So the magnitude of V is just the square root of 64 plus negative 5 quantity squared, right? It's not, don't square it and then make it negative. And that's, what's that, square root of 89? Square root of 89. Okay? Yes, the magnitude of V. That means a magnitude with two little bars on it. Okay. Two more things, then we're gonna keep going. Are you excited about that? We got it. It's just good. Okay. A unit vector. Unit vector is a vector.
So can you go back a slide for a second?
Yeah. Christian, that's a bad note-taking tool. That looks cool. Should I pause and tell a joke?
Sure.
Yes?
Where did you get the V1 and the V2 for the magnitude?
So this is V1
Oh,
and this is
okay.
V2.
Thank you.
Okay? A joke.
Yeah, hit us up.
How do you catch a polar bear? Oh, this is my favorite joke. I never told you how you catch a polar bear. You go to the North Pole. Ah! Are you copying me? You're going to tell my daughter, and then I'm going to get in trouble at home. Okay. Okay. You go to the North Pole, because I'm going to get fired for telling dirty jokes in class. This is not really a dirty joke, but it's a marginal joke. You go up to the North Pole, and you dig a hole in the ice. You've heard this, Matt, when you're a freshman probably, or, I don't know. And you dig a big hole in the ice, North Pole, and then you put peas all around the outside of the hole. And then you wait, and you wait, and you wait. And then finally, when the polar bear comes to take a pee, you kick him in the ice hole. That's my favorite joke. Okay. That's semi. Okay. I got some laughs out of that one. That's because I didn't make that one up. Yes, ma'am. Yes. Okay. That's my polar bear joke. Okay, a unit vector. Oh, you've heard that before? Been on pause. Oh, what are you gonna do? So, you people. So now I'm gonna teach you the same thing again. Okay. So you people in the viewing audience, you missed some gaps. So you can look at that. There you go. I talked about that stuff. All right. Next one. That's we're adding vectors together. Okay. It's not that hard. You'll figure it out. Okay.
See this? Yeah, look at that.
If I wanted to do u minus v, okay, that's equal to u plus negative v, right? So the way I would do that graphically, you could do it algebraically. You would just take this plus the opposite of this, yes? But graphically, what it would look like, here's u, and minus v would be going the same magnitude but in the opposite direction of that, right? So if that's v, negative v would look something like that, right? Negative v, and the resultant of u minus v would be something over this way from here to here. So this vector here might represent u minus v. You understand that? Okay? And so if this is u plus v, this would be u minus v. Okay? So if I have, here, let's give you guys one to try to do. So if I have, do you want me to go back? Is that okay? We're good? We're almost done. Promise. Okay? So if I have something, let's do one more example, then I'm going to list some of the properties, and then we'll be done. So if v is equal to negative 2,5, and u is equal to 3, 4, and they say something like find v minus 2u, v, whoops, that should be a minus sign. v minus 2u, all you do is you, algebraically, it'd just be negative 2, 5, minus 6, 8, right? Which is negative 2 minus 6, which makes negative 8, comma, 5 minus 8 makes negative 3, okay? Graphically, the way that looks, let's put arrows on both ends. Graphically, you would take v. I'm just going to do this real kind of faking it. V, which would be let's change color. So v would be back 2 and up 5, right? Back 2 and up 5. So say this is v, something like that. And then I'm going to subtract 2u. So 2u would normally go over 3 and up 4. So instead I'm going to go back 3 and down 4, but I'm going to do that twice, right? I'm going to go down 3 and back 4 once, and then go back 3 and down 4 again. And then my resultant, let's see if I got close, okay? My resultant would look something like this, right? Which would be back 8 and down 3, right? See that? Which kind of looks pretty good graphically as well. See that? Okay, so here's u, or v, right? And here's one u, one negative u, another negative u, and so this is v minus 2u right there. So this one here, so this is v minus u, and so this is v minus 2u. Here's to you. Here's to you, Mrs. Robinson. Oh, sorry, I get distracted. All right. So the last thing, the very last thing is properties, and this is just stuff to know. So properties of vectors, is it's just like commutative property and association. So u plus v is equal to v plus u, which I talked about earlier. And that, what's that one called? I think that's called the commutative property. You don't have to worry about what they're called, but you just, okay? The other thing, so it doesn't matter which order you add them in, okay? The other property is u plus v plus w is equal to u plus v plus w, which is equal to u plus v plus w. That's called associative property, right? You can group them in any order. So you could take u plus v and add it to w, or you could take u and add v plus w to it. So it doesn't matter how you group them. That's called the associative property. You have something called the zero addition property. So if you take a vector u and you add 0 to it, you still get u, okay? And that kind of makes sense. What if I take u and I add negative u to it? What do you think I get? 0, right? Because that's like saying, okay, I start off going one vector from here to here, and then I go backwards the opposite direction. I'm going to end up in the same, I'm going to end up back at 0, right? Then just two more things on scalar multiplication. C, so C and D are scalars, meaning numbers. If C and D are scalars, and U is a vector, then C times D times U is equal to CD times U, okay? Meaning, if there's a number out in front, if like it's 5 times 3U is equal to 5 times 3 times U. And likely also like that, C plus D is kind of like the distributive property. C plus D times u is equal to, hey, cu plus du. Hey, it's like two colleges, right? Go cu. So if you have two scalars, so say this is like 5 and this is like -3 or something like that, and this is some vector. So pretend that that's -1, 4 or something like that. So what this says is I can add these together and then multiply this by this vector, or I can multiply c times u and d times u and then add them together, okay? And that's all that's in. And that's it. And that's the end. Thank God, okay? So that's the end. You can